3.6 on pavement materials part 3. This is the 6th lecture in the module pavement design. In this lesson, we will be dealing with bituminous binders. The specific objective of this presentation is to make the student learn about different types of binders used in pavement construction, learn how pavement grade bitumens are produced, and also make the student appreciate the requirements of good paving binder. It is also expected that the student would learn about the determination of important characteristics of bituminous binders which affect pavement performance. There are various types of paving binders. As we understand from binder, this is a material that is used to bind. We are especially talking of pavement binders that are used in flexible pavements, where we normally use bituminous binders. Of course, in cement concrete pavements, the binder used is cement, and in other stabilized layers, we can use lime and other types of binders. Since we are talking about flexible pavements, the binders that we are going to be talking about will be bitumen and other related materials. So, we have in this list bitumen, tar, cutback, emulsion and modified binders. We will be talking about all these binders in this lesson and the subsequent 2 lessons that will be following this particular lesson. Let us first talk about bitumen and tar. I am talking about these 2 terms together because often these 2 are confused for each other. Rather, most people do not understand the differentiation between tar and bitumen. Bitumen, of course, is the most commonly used binder that is used nowadays, whereas tar is hardly used nowadays. We have to understand that bitumen and tar are 2 distinctly different materials of different origins, having different chemical composition and naturally different physical properties. Bitumen is a dark brown to black color naturally occurring, or a material that is produced by petroleum distillation. So, bitumen occurs naturally or can be produced by distillation of petroleum, which is dark brown to black in color, whereas tar is manufactured from destructive distillation of bituminous coal. Tar is very highly temperature susceptible compared to bitumen, and its use is more health hazardous compared to the use of bitumen. We use the term temperature susceptibility. We will be discussing about this term in greater detail in subsequent slides. What we mean by temperature susceptibility is the properties of tar change more significantly with variation in temperature compared to what would happen to bitumen for similar variation in temperature. At times, for specific purposes, we do not want the binder properties to be changing so significantly. We know the properties of bitumen and then tar are going to be different at different temperatures, but we do not want these materials to be undergoing quite drastic changes with variation in temperature. Tar, of course, is not regularly used nowadays because it is not that easily available, and its properties compared to bitumen are not that good as far as pavement construction is concerned. So, our discussion will be mostly focused on bitumen and bituminous binders. There are various terms that we commonly use. Before we understand each one of those terms, it is important to appreciate that the adhesive and waterproofing qualities of bitumen have been known for a long time. Of course, bitumen is in pavement construction and other areas mostly for its adhesive characteristics and waterproofing characteristics. Bitumen has been used in shipbuilding industry in Sumeria as early as 6000 BC. Various terms that we normally use in describing these binders are bitumen. This refers to the viscous liquid, it can be in solid form also depending on the temperature at which it is maintained, consisting essentially of hydrocarbons and their derivatives, and soluble in carbon disulfide, substantially non-volatile. This is a material which softens when heated and it is black or brown in color. This is the general description of bitumen. The American term, the term that is used in American literature for describing this material is asphalt, whereas asphalt has got a different meaning in British literature. Petroleum bitumen is that bitumen that is obtained by refining petroleum. We will discuss about refining process of petroleum and how bitumen is obtained. So, petroleum bitumen is that bitumen which is obtained by refining petroleum. Natural bitumen is that bitumen which occurs naturally as deposits in lakes, a typical example or famous example being the lake asphalt in Trinidad. It can also occur as rock asphalt, as rock deposits. Straight run bitumen is the bitumen that is produced by petroleum refining, whose viscosity has not been adjusted by blending with other materials or by softening it by with cutback or other solvents or any other method. So, this is the bitumen that comes straight out of the refinery or processed byproduct that comes as after refining the petroleum, and which has been not whose viscosity has not been adjusted by adding any solvent or any other material. Blown material is a straight run bitumen, but which is further treated by blowing air through it when the bitumen is in hot condition. The bitumen which results out of this process is called as blown bitumen. Zilsonite is a hard variety of naturally occurring bitumen which is black, very hot and brittle. This is a material often used to add to normal bitumens to increase their hardness, increase their stiffness, but as it is, zilsonite by itself is not normally used in any pavement construction. Asphalt is a term, as I indicated, in British literature to represent the mixture of bitumen and inert material which are aggregates. So, asphalt in British literature is indication of rather it indicates a mixture of bitumen and aggregates, whereas in India and many other countries we use the term bituminous mix, which again is a mixture of bitumen and inert matter which are aggregates, and various terms that we use for bituminous mix depending on the composition, depending on the content of bitumen that we use are bituminous concrete, dense bituminous macadam, bituminous macadam represented by BC, DBM, BM and so on. As I said, the most of the bitumen that we use currently is obtained by refining crude oil. The crude composition varies from source, rather it varies with source. Hence, the quantity and quality of bitumen that can be obtained from a given source will also be different. The residual bitumen, that is the quantity of bitumen that can be obtained from different sources of crude, varies from about 1% to 60% depending on the crude type. Paraffin type crude yields waxy bitumen. This is a bitumen which contains high percentage of wax. Especially the crude found in the west coast of India, that is Bombay and Gujarat, contains higher wax content. We will subsequently discuss the implication of having high wax content, which is in terms of its temperature susceptibility. This bitumen having higher wax content is going to be very brittle, very hard at lower temperatures, but it is going to be very soft at higher temperature. So, depending upon the content of wax that is going to be there in bitumen, the properties are going to be changing significantly with variation in temperature. Naphthenic crude yields usually wax free bitumen. The Assam crude and the Middle East crude yields good bitumen as far as wax content is concerned, and also as far as the performance when used in pavement construction is concerned. Refining of petroleum crude is usually done by fractional distillation. Petroleum crude consists various components having different boiling points. As a result, these constituents are separated by fractional distillation process. Since bitumen is the one having the highest boiling point among these fractions, it is the residue that is going to be available after the distillation process is complete. This is a schematic arrangement of the first step of refining of crude, which is atmospheric distillation. Here the crude is fed into this and then heated and then fed into this tank. So, the volatile matter as the lighter fraction get evaporated first and then they reach the top and then get condensed here. There is a arrangement for condensing those vapors and then an arrangement to remove the condensed material. So, obviously, the material having lower boiling points is collected at the top, gasoline which we call as petrol, then naphtha, kerosene, light gas oil, heavy gas oil, and what is going to be remaining at the bottom is the long residue. Possibly in terms of commercial value, all these materials may be of much greater importance compared to what is available at the bottom as long residue. But the long residue is not a material that can be directly used for pavement construction. This requires further processing because it would still contain certain amount of gas oil and other components. So, this again has to be distilled, but further distillation is done under vacuum. So, this is the amount of vacuum that is applied, and these are the components that are going to be produced, and what we are interested in is the short residue that is produced. This could as well be the penetration bitumen or the paving grade bitumen. We can get bitumens having different consistency at the end of vacuum distillation. It is possible to use them directly depending upon what type of a material is available, what consistency could be attained, or it may require further processing before the same can be used in pavement construction. As we see here, short residue often has to be blown to get the commonly used pavement grade bitumens. Blowing is the process of, as I told you earlier, blowing air into the bitumen when it is in hot condition. but we normally go for semi blowing to obtain penetration grade bitumens. We also go for further full blowing. Whether it is semi blowing or full blowing depends upon the duration of blowing, temperature at which the blowing is done, and other conditions. The fully blown material is not normally used for pavement construction. It is used for possibly roof treatment and other industrial purposes. But what we normally use is either the short residue or the semi blown bitumen, from which we can get bitumens of different penetration or different consistency. The short residue has a penetration range of about 35 to 300, that means about 3.5 millimeters to 30 millimeters penetration. We will discuss about the term penetration subsequently, but penetration is a term that indicates the consistency. 35 penetration is a harder grade, whereas 300 penetration is a softer grade. So, a wide range of penetrations can be obtained after short residue depending on the distillation process. The short residue, as we indicated in the previous slide, is normally further processed or further modified by air blowing. Air blowing is the process of passing air through the hot short residue at about 240 to 320 degrees centigrade. What happens in blowing is actually normally the oxidation process that takes place. The oxidation converts the relatively low molecular weight fractions called as maltins into higher molecular weight fractions known as asphaltins. Blowing normally reduces the penetration, that is, it makes the binder harder, increases the softening point, another term used to describe the consistency of the binder. It also lowers the temperature susceptibility of the binder. That means the properties of the binder are not going to be changing significantly with variation in temperature if these binders are blown. Bitumen is a very complex chemical mixture of molecules that are predominantly hydrocarbons. It is normally very difficult to find out the exact composition of bitumen, and for most practical purposes, as far as pavement engineering is concerned, knowing the exact chemistry of bitumen has not been found to be of great importance, because the performance has not been significantly been correlated to the bitumen chemistry. So, the effort of doing very complicated testing process to find out the exact chemical composition of bitumen has not been found to be worth. However, whatever literature indicates to us tells us that these are predominantly soluble in carbon disulfide. It is mostly in colloidal state. Its composition typically is carbon 82 to 88%, hydrogen 8 to 11%, sulfur 0 to 6%, oxygen 0 to 1.5%, nitrogen 0 to 1%. One can also find traces of metals such as vanadium, nickel, iron, magnesium and calcium and so on in bitumen. As I just mentioned, complete chemical analysis of bitumen is very difficult. The bitumen constituents are broadly classified as asphaltins, resins and oils. Asphaltins are dark brown friable solids. They have high polarity and interact or associate more active. These are the active constituents of bitumen, and these are mainly responsible for viscosity of bitumen, stiffness of bitumen and other engineering properties of bitumen. Typically, the percentage of asphaltene in bitumen can vary from 5 to 25% depending on the source of crude and also the process that is adopted to obtain this paving grade bitumen. That is how the distillation is done, how blowing is done. Depending on all these things, the percentage of asphaltene can vary from one source to another one. Higher asphaltene content results in harder viscous bitumen with low penetration and high softening point. The next component, which is resins, is a dark semi-solid to solid material which is fluid when heated and brittle when cold. This is the material that disperses asphaltene particles or asphaltene matter throughout the oils. Oil is the other component that bitumen has. So, the asphaltene dispersed in oil with the help of the resins to provide a homogeneous liquid. When these asphaltenes are, rather the resins are oxidized by various processes, they get transformed into asphaltenes. So, you can find that compared to normal bitumens, bitumens having oxidized or aged or blown have more percentage of asphaltenes compared to the original bitumen. The other component is oil, which is a colorless liquid and which actually is the medium in which the asphaltenes and resins are in a colloidal state. These oils yield asphaltenes or resins on oxidation. Depending upon how much oxidation takes place, oils can get converted into resins or in turn it can get converted into asphaltenes. Accordingly, the properties will change. Bitumen is considered to be a colloidal system consisting of asphaltenes, resins and oils. Before we understand the properties of bitumen and the need to characterize this particular material, let us understand where this material is used in pavements, what is the requirement of each one of those components of pavement, and accordingly what properties the binder should have if it is used in a particular location or particular part of the pavement. Typically, bitumen is used in different parts of pavement. It is used in interfaces between bituminous layer and granular layer, between two different bituminous layers as you see here, but these are very thin layers and which are formed by spraying the bitumen on the surface. So, this is one aspect. You should have bitumen which can be sprayed and which will bind two different layers. These two different layers can be granular and bituminous or bituminous and bituminous. Other than this, we use bitumen in bituminous courses, bituminous binder course and bituminous surface course. Surface course is usually a thin layer ranging from 20 millimeters to 40 or 50 millimeters. Typically, bituminous concrete is provided as 40 to 50 millimeter thick. This is a surface layer provided to cater to the demands at surface, whereas bituminous binder course is the main bituminous layer, main structural layer, which provides longevity to the pavement. So, the requirements of bitumen in a binder course and requirements of bitumen in a surface course are definitely different, because surface course is subjected to different conditions and binder course is subjected to different conditions. So, we have to understand these parameters or these requirements of bitumen when it is used in different components. So, the main applications are it has to be used as spray at interfaces and in bituminous mixes either in binder course or in surface course, either in thin layers or in thick layers. When we study bitumen, there are various aspects of bitumen that we need to understand. These are, we have to test the binder for its purity, because as somebody who is using the binder in pavement construction, we have to ensure that good quality bitumen is being supplied. So, what is expected of a pure bitumen we should know, and how to test for its purity also we should understand. Next thing is the aspect that is related to safety in handling the bitumen, because bitumen is going to be heated, and when heated, whether it is safe to use, at what temperature it is safe to use, we have to understand that. We have to have some idea about the cohesive properties of bitumen, also understand the adhesive capability of bitumen to aggregates that we are going to use in a particular project. These aggregates could be of different nature. We also have to understand how workable bitumen is going to be, or how fluid, or what is the consistency of bitumen for different operations. If we want to spray it, can bitumen be used as it is at normal temperature? Can we spray it? Or can bitumen be mixed with aggregates at normal temperatures? Obviously not. So, we have to understand what is the fluidity that is required for a spraying operation, what is the fluidity or consistency required so that it can be mixed with aggregates, so that it can be laid in a pavement layer and then compacted. So, different operations would require different consistencies or fluidity. We have to understand this aspect, and we should also be able to quantify the consistency and then have specifications for different operations. Another important aspect is the binder has to be durable during service life of a pavement. We should not have we cannot have a binder which undergoes drastic changes within 4 to 5 months time, and because of the climatic conditions itself, and because of what it is subjected to during its service life, it lasts only for 4 months, 6 months, and as a result it undergoes so many changes and the pavement starts failing. We do not want to have such situations. So, the binder that we are going to have should be sufficiently durable in terms of its properties, and we have to have specifications as to what can be the change that can be permitted over some time period, what is an acceptable durable binder. So, we need to understand this aspect. When we study bitumen, we by now understand that bitumen is a material whose properties vary with temperature. So, there are different temperatures at which we have to study this material, because bitumen is going to perform, bitumen is going to be used at different temperatures, starting from its construction operation to its service life. These temperatures are we need to understand the behavior at high service temperature. Service temperature is the temperature of the pavement during its service life period, maybe 10 years, 15 years, 20 years. So, what are the higher temperatures that the binder or the bituminous pavement is going to be subjected to? Typically, this can be 20, 30, 40, 50, it can even be 70 degrees centigrade if we are talking about areas which are very having hot climatic conditions. And we are also interested in understanding the behavior of binder at low service temperatures in winter. Possibly we are concerned about this, especially when we have low temperatures as low as -10, -15, -20. So, bitumen is going to have different properties. So, the bituminous mix is going to have different properties. We are going to be concerned about that. And bitumen at average service temperature, this can be 25, 30. We are not talking about very high temperatures, we are not talking about very low temperature, we are talking about average temperature. This is the temperature at which the bituminous pavement is going to carry a large number of repetitions. Very high temperatures are going to be there maybe 1 week in a year. Similarly, very low temperature is also going to be there for a very short time period, but most of the time period the temperature is within a middle range. That is the time period during which most of the loads are going to be applied. So, we need to understand the behavior of bitumen at that temperature range. Similarly, we also need to understand the behavior of bitumen at very high temperatures associated with construction activities, because we are going to heat the bitumen to 150, 160, 170 degrees centigrade for mixing it with aggregates and then laying it. So, how bitumen behaves at these high temperatures also needs to be understood. We can see the behavior of bitumen with time and temperature, as bitumen is a viscoelastic material, hence its properties are going to be dependent on temperature as well as rate of loading. The sketches here illustrate in a simple manner what is going to happen to the bitumen with time and temperature. The first sketch is, let us say, when the bitumen content is stiff at a temperature of 25 degrees centigrade. After 1 year, let us assume this is the amount of flow that we observe, but same binder at the same temperature after 4 hours is going to be flowing much further, but similar amount of flow can be obtained within shorter duration of 1 hour, but at higher temperature. What this indicates to us is the flow of bitumen is a function of time period that we allow and also the temperature at which the flow is allowed. The temperature and loading time are very important for studying bitumen properties. Whenever we talk about a test that is to be conducted on bitumen to understand its engineering properties, we always specify the temperature at which the bitumen is to be tested. The typical temperatures that we normally consider for testing bitumen are 25 degrees centigrade. This is considered to be the average temperature of pavement. It does not have to be true for all locations, all places, but typically this is the average temperature. So, many of the tests are conducted at a temperature of 25 degrees centigrade. Maximum temperature of pavement, maximum service temperature, that is normally considered to be 60 degrees centigrade, although we now know that the maximum service temperature can be even much higher than this. Maximum mixing, pumping or spraying temperature, for all these operations, to understand the behavior of the bitumen, we normally use a temperature of 135, or in some tests we also use a temperature of 150 degrees centigrade. For testing purity, there is a simple test. Pure bitumen dissolves completely in carbon disulfide. The percentage of insoluble material after it is dissolved in carbon disulfide, the percentage of insoluble material indicates the purity or rather the impurity of the material. Bitumen also should be free of water, because the presence of water in bitumen causes foaming at high temperature. So, there is a water content test for this. To understand the safety of bitumen when it is operated at higher temperatures, because bitumen is going to be heated to higher temperatures as high as 180 to 180 degrees centigrade, it should be safe to handle bitumen at such high temperatures. There are couple of tests that are done to identify whether bitumen is having hazard when it is heated to such high temperatures. Flash and fire point are two different temperatures, tests we conduct. Flash point is the temperature at which bitumen gives off vapors which ignite in the presence of flame, but vapors do not burn. On the other hand, fire point, beyond this flash point temperature, if you continue to heat the bitumen, the vapors start igniting after certain temperature in the presence of flame and continue to burn. The temperature at which the vapors start igniting and then starting to burn is fire point. In this, the commonly used test method is a Cleveland open cup COC apparatus method. In this, the bitumen is heated gradually. As the vapors come, fire is put to that, and then if you can observe a flash, that is a flash point test, flash point temperature, and the temperature at which the vapors start catching fire, that is the fire point temperature. To understand the consistency or fluidity of bitumen at different temperatures, there are a number of tests that can be conducted. Consistency is nothing but the degree of fluidity at a particular temperature. Penetration test is the simplest that is conducted, in which we determine the penetration of a standard needle into the bitumen under the weight of a standard mass, and the needle penetrates for a standard time period. The standard conditions are weight including needle and other weights that we attach is 100 grams, standard time is 5 seconds, and standard temperature normally used is 25 degrees centigrade. We can of course conduct this penetration temperature at different other temperatures also. The penetration is expressed in terms of 0.1 millimeters. For example, 80-100 penetration grade bitumen, where the bitumen is represented in terms of its penetration range, can have penetration ranging from 8 to 10 millimeters. There is a simple schematic arrangement of penetration test. On the left hand side, which is at the beginning of the test, the needle just touches the surface of the binder, and this is the mass including the weight of needle. After 5 seconds, the needle penetrates into the bitumen. This is what we are trying to measure, and this is the penetration at this temperature. This is a simple apparatus that can be used for conducting penetration test. There is a dial which indicates the penetration. The sample has to be prepared and conditioned in air and in water so that it attains the standard temperature of 25 degrees centigrade. There are specifications available for carrying out these tests. The test can also be conducted at 4 degrees centigrade, but with a much heavier weight, which is 200 grams, and for longer time period, which is 60 seconds time. And the penetration ratio, which is the penetration at 4 degrees divided by penetration at 25 degrees centigrade expressed as percentage, is often used to express the temperature susceptibility of the binder with variation in temperature. For higher test temperatures, obviously we need to use longer needs, bigger cups. Typical penetration grades of bitumens that we normally use are 30-40, 60-70 and 80-100. Another very important test that is conducted on bituminous binder is softening point test. This is also called as ring and ball test. Softening point is the temperature at which the binder attains a specified consistency. As we know, bitumens are viscoelastic materials with no sharply divided melting point. Hence, the softening point is evaluated corresponding to an arbitrarily defined condition. What is this defined condition? Let us see in the next slide. What is done in this case is a bitumen disc is formed by pouring bitumen in this ring and then subjecting it to very low temperature so that it becomes hard, and then putting a steel ball over the bituminous disc, and then we start heating it from a initial temperature of 5 degrees centigrade. So, the ball starts moving down as the bitumen becomes softer. So, once the ball moves by a distance of about 25 millimeter, the temperature at that point, this is the defined condition of consistency that we are talking about. The rate of heating is at 5 degrees per minute. The temperature that is attained at that condition is the softening point of bitumen. Typically, the softening point of a 60-70 grade bitumen ranges from about 45 to 70 degrees centigrade. There is a typical arrangement that can be used. Of course, I have not shown the complete heating arrangement and other things. We have the frame and we also have the rings, and balls are shown on the left hand side. Ductility is another useful test that is conducted on bituminous binders, which gives a measure of the tensile properties of the bitumen. This indicates the ability of bitumen to deform when it is subjected to load. If the binder does not have adequate ductility, it is more likely to crack when extended, because bituminous mixes, bituminous binders, when they are flexed in thin films, are going to be flexed, they are going to be elongated. If it is not capable of being elongated sufficiently, it is going to crack. So, this is the test that tests how long the bitumen can be extended or elongated before it cracks. So, this property is determined by stretching a bitumen briquette of standard shape at a standard rate of pull, and at a standard temperature. This is the standard briquette that we use, having a minimum size of 25 by 25 at its neck, and this is extended at a rate of 50 millimeter per minute. Normally the test is conducted at 27 degrees centigrade. So, the briquette is extended at this rate, and when it breaks, when the thread breaks, we measure what is the distance by which it has been extended, that is the ductility of the bitumen. This is a typical ductility apparatus that we have. On the left hand side we have the briquette. You can see it is in a dumbbell shape and having a minimum cross section at the center. Right hand side we have an arrangement which can be used to pull this or elongate the bitumen briquette. There is a frost breaking point test that is normally conducted on bitumen, although it is not very usual for all climatic conditions. This is relevant for climatic conditions where we can get low temperatures as low as maybe -10, -15, -20. This indicates the stiffness of bitumen at very low temperatures. As I indicated, this is relevant for only those locations having very low temperatures during, obviously, in winter season. The bitumen should not be too brittle at low temperatures, otherwise when they are flexed or pulled, it is going to be cracking very easily. Okay. That is what is known as low temperature cracking. The temperature at which a thin film of 0.5 millimeter thick bitumen cracks when flexed, that is what is known as frost breaking point. This is a temperature. Typically what is done is, there is a steel plate on which the bitumen is coated, 0.5 millimeter bitumen film is coated on the steel plate. The temperature of the bitumen is gradually reduced to very low temperatures, and then we keep on flexing the bitumen. The temperature at which the bitumen film gets cracked, that is its frost breaking point temperature. And the most important property that we need to study about bitumen is its viscosity. Bitumen tells us about its fundamental rheological behavior of bitumen. Rheology is a study of flow and deformation of materials. Viscosity gives us an idea about the rheology of bitumens. Viscosity, as we have studied in other subjects, is the resistance offered by a fluid to a shearing force, which is opposite of fluidity. It is necessary to learn about the flow and deformation of bitumen binders at different temperatures corresponding to construction and also the surface temperatures. Viscosity at high handling temperatures, that is at 135 degree centigrade and 150 degree centigrade, and at high service temperatures, typically at 60 degrees centigrade, is of interest for us. We are of course also interested in the viscosity that bitumen attains at low service temperatures. Low service temperatures can be as low as -10, 15. The dynamic or absolute viscosity is defined as given below. What we see here are two parallel plates. One of the plate is fixed. There is a bitumen film that is sandwiched between these two plates. The bottom plate is fixed. The top plate is moved at a constant speed of velocity of v. The force that is required to, shearing force that is required to move the top plate at a constant velocity of v is, let us say, F. Let us say the thickness of film is d and the area of binder film is, let us say, A. So, the force required to move the top plate at a velocity of v is proportional to area, it is proportional to the velocity, and it is proportional to, this should be proportional, and it is inversely proportional to the distance, rather the thickness of the film. from this we get viscosity or the shearing force using a constant of proportionality, where this is the viscosity. So, by rearranging these terms we can get viscosity, which is absolute or dynamic viscosity, as the shearing force multiplied by thickness of film divided by area of the film and velocity at which the film is or the top plate is moved. F by A is the shear stress and V by D is the temperature velocity gradient within the film thickness. The units of absolute viscosity in SI units are Newton second per meter square or Pascal seconds. In CGS units it is in poise. 1 Pascal second is approximately equal to 10 poise. Measurement of absolute viscosity, we normally use what is known as a sliding plate viscometer, which operates on the basis of the fundamental principle of the definition of absolute viscosity. In this, bitumen film of known thickness is sandwiched between two parallel plates. The test is conducted at a selected temperature and at a selected rate of shear, that is velocity. The force required to move the plate at a velocity of V is measured. This is a typical setup used for determining the absolute viscosity using a sliding plate viscometer, but more commonly used viscometer that is being nowadays used is a rotational viscometer. In this, the absolute viscosity is obtained by measuring the torque offered by the fluid to the rotation of a spindle at a given rotational velocity at a given temperature, and this has to be measured. Once we measure this torque, we can calculate what is the absolute viscosity of this bitumen. This is a Brookfield viscometer, photograph of a Brookfield viscometer, which is a rotational viscometer, which is most commonly used for nowadays for determining the absolute viscosity. To summarize, in this lesson we have learnt about different types of bitumens, binders used in pavement construction. Although we have not discussed about all those types of bitumens, we have listed bitumen, tar, cutbacks, emulsions and modified bitumens, but in this lesson we have only discussed about bitumen. We also talked about tar, but since tar is not going to be extensively used anymore for pavement construction, so our discussion of tar is not going to be there any further. So, we are going to talk about bituminous binders only, and in today's class we have talked about only certain properties of bitumen, and we are going to be continuing in the next lessons about other properties of bitumen. We have also discussed about the process of refining of crude petroleum and the production of bitumen from this refining process. We have discussed about the chemical composition of bitumen, and we have also learnt about various test methods and procedures for evaluating the rheological behavior of bitumen. Although, as I said, we have not talked about the complete testing process of bitumen. There are other methods that we are going to be discussing, other aspects of bitumen that we are going to be discussing, but that will come in the next few lessons. Let us take up a few questions from this lesson. Is tar different from bitumen? What is zilsonite? Next question, how do the properties of bitumen get affected by the process of blowing in refinery? What are the temperatures we are normally concerned with while studying the behavior of bitumens? What are the standard test conditions for penetration testing of bitumen? These standard test conditions I am not referring to the conditioning of binder before we actually conduct the test, but what are the actual testing conditions? What is the significance of frost breaking point test and what is the significance of ductility test? Now, let us have some answers for the questions that we asked in lesson 4.5. If you remember, lesson 4.5 was about aggregates. What is meant by hydrophilic aggregate? As we discussed in the last class, some aggregates have more affinity to water compared to its affinity to bitumen. These are called as hydrophilic or water loving bitumens, or rather water loving aggregates. Usually these are acidic in nature. These are normally siliceous aggregates, typical examples being sandstone and quartz. If we have aggregates that are hydrophilic in nature, these are problematic as far as stripping of aggregates is concerned, because they love water more than their love for bitumen. As a result, it would be more easier for water to replace bitumen from this aggregate and then cause stripping. The next question was, define nominal maximum aggregate size. For a given gradation, nominal maximum size is the largest sieve, size of the sieve, that retains some of the aggregate particles, but the retained portion is not going to be more than 10% by weight. The next question was gap gradation. Gap graded aggregates normally contain only a small percentage of aggregates in the mid size range. As you can see from the sketch, the mid size range, the percentage passing is more or less constant. That means those fractions are more or less missing. What we have more is the smaller fractions and the larger fractions. So, as a result, these aggregates have more air voids, they are usually less workable, and they usually have the potential for segregation. That means the larger particles will come to one place, the smaller particles will go to another place. So, there will not be uniform mixture of different sizes, all sizes throughout the medium. The fourth question was, how is the combined flakiness and elongation index determined? As per the MORTH recommendations, we know how flakiness test and an elongation test is to be conducted. Flakiness is determining the percentage of particles with least dimension less than 0.6 times the average dimension of a particular fraction. This we discussed earlier. Similarly, elongation is to identification of particles whose maximum dimension is more than 1.8 times the average dimension of a given fraction. So, as per MORTH recommendations, what we have to do is we have to first conduct the flakiness test, then collect the non-flaky aggregates, then we have to conduct the elongation test on those non-flaky aggregates. Then we have to add the two indices, that is the combined flakiness and elongation index. The fifth question is, what is the difference between the apparent and then bulk dry specific gravity? In fact, we wanted to know about dry specific gravity only. If you look at these two sketches, the left side aggregate is a dry aggregate without any moisture. There is a pore on the surface, but there is no moisture there. On the right hand side, we have the same aggregate, but the pore is filled with water. To calculate apparent specific gravity, we use dry mass. In fact, we use dry mass in both cases, both for apparent specific gravity and bulk dry specific gravity. But what is different is the volume that we use for calculation. The volume of water replaced by dry aggregate, in fact, that this is the volume excluding the volume of the pore that is there on the surface. If you can determine this, that will give us apparent specific gravity. Whereas for calculation of bulk specific gravity, which is dry bulk specific gravity, we have to include the volume of the pores that are there on the surface, which can be penetrated by water. So, if we include that volume also, that becomes the bulk volume, then we get bulk dry specific gravity. But we can also get bulk saturated surface dry specific gravity, wherein the volume is similar to bulk dry specific gravity, but the mass is saturated surface dry mass, wherein it is a saturated aggregate, the surface water is removed. So, that is what we have here. So, that was the last question. Thank you.